vortices, and then SU stands most probably, at that time he was in Stanford University. Then you can do vortex manipulation using scanning squid, so you can trap vortex with this loop, you can drag it, and then again you can write something, you position the vortex, and then you write also another abbreviation of another university. Then you can do it with optical manipulation, and AV stands for abricos of vortex, so you create with optics a hotspot, and the hotspot works as good pinning center. Then you place there the vortex, you create the next pinning site, and then you get something like that, AV here. Then basically you can also probe the pinning strength by trying to drag these vortices, and of course it comes back to these pioneering experiments with single atoms. Here the scale is much bigger, but objects are quantum objects, so you deal with quantized vortices. Here you deal with individual atoms. So then local heating effect. So remember that I told you that we have actually close to our scanning hole cross, we have a bad tip. So we have gold metallization. And we can use this gold metallization, and then we have, instead of one probe measuring local fields, we can have also STM next to it. So in principle, we can then measure tunneling and local fields simultaneously. So that's actually what we can do. And then you can use STM tip to generate local heating in the sample. This is also a well-known application of STM tips, that if you send relatively strong tunneling current, then you can create local, very small hotspot. And then we were using these hotspots in order to trap the vortices. So other groups have been using, of course, STM tip to create local hotspot, and it works pretty well, judging from numerous publications in the literature. So what about this scanning hole? So that's what I told you exactly. So we didn't make it intentionally, but here you always have some protrusions of gold when you deposit, and it acts as STM tip. And next to it, you have this hole cross. So on a single sensor, you have two, actually. This very low quality STM tip and quite high tech, this scanning hole probe. But this guy helps us to navigate, but also we have used it to create hotspot in a superconductor. And that hotspot was able to trap vortices. We can use this STM as a local heater, and then we use hole probe to image magnetic field distribution and distribution of vortices. So then, this is before creating a hotspot with STM tip. Then you heat it, and then after applying tunneling pulse, you create a hotspot, and there you trap the vortices. So this is like sort of quenching something very strongly, and the thing is that in some numerical simulations, theorists compare this process with quenching process in early universe. So immediately theorists are jumping to Keeble-Zurich scenario for formation of objects in our universe. And actually, some arguments from that are applicable to situation here. So then, depending, of course, on bias voltage, you can create very small spot, bigger with bigger bias voltage, and then you have vortex clusters here, and here you have vortex rich area, and here you have vortex poor area. So then you can actually induce cluster. Yeah.
So the image we are looking, this is topography, or this is density of state? Or what are we looking at this?
No, these are vortices scanned by scanning hole probe.
This is just direct?
Yeah, so this cheap STM tip is used only to generate heat pulse, tunneling pulse. And after that, forget about it.
This is a big vortex.
This one, it consists of small vortices. They're singly quantized. So. And then,
It's a cluster of vortices.
It's cluster of singly quantized vortices. This one. It's not a big vortex. If you generate much bigger sport, then you can stabilize giant vortex and then it decays into singly quantized vortices. But I don't have slides for that here. Okay, so then you can warm up the sample closer to TC, and of course this one is relaxing to more or less homogeneous distribution of vortices. So in theoretical modeling, we have used local heating model, and with that you can also first see equilibrium distribution, then you have situation during tunneling, and after tunneling the whole situation basically reminds what we have seen in experiments, and then this quenching and reminds, as I have told you, Kibble-Zurich transition for the universe. When universe started to be cooled down, then it happened not everywhere homogeneously, but cooling process was very inhomogeneous, but in the end it was becoming more and more homogeneous, but in the beginning the picture was something like that. And other groups have been actually working on similar subjects, and for example in experiments in these publications you can also generate vortices and antivortices by using different modes of quenching of the vortex method. And then in our simulations you see that also you have individual vortices, but they are forming clusters, and these clusters, at least quantitatively, they remind the situation we observe in experiments. So then it was of course attempting, as well as for other groups as for us, to write something by manipulating individual vortices with a STM tip. So we did it also, and V stands here not for Victor but for vortex, don't worry. So I didn't make these experiments myself. Okay, so you see these vortices and you can drag them with STM, like here. You can merge them, then this becomes doubly quantized vortex, and then it can disintegrate again from doubly quantized to two singly quantized vortices. And this is advantage of scanning whole probe, because we know exactly distribution of fields and we know exactly how many flux quanta each vortex is carrying. So that's just snapshots scanning whole probe microscopy to demonstrate this vortex manipulation. This is doubly quantized vortex. It's moving back again here, and then it disintegrates again into two singly quantized vortices. And then dragging, we have written this V for vortex, and like many other groups, we have shown that with scanning whole cross and with this heating with our cheap STM tip, you can drag vortices individually, one by one, and doing that you can do some vortex manipulation. Okay, so where are we now? Okay, so this we have seen. Basically, I briefly mentioned that in the first part that this antidot lattice we will use now to see formation of vortex, antivortex dipoles, because if you send through that Meissner current, you know exactly the location of all pinning centers. But at the same time, it generates a very nice spinning landscape, and this makes it possible to realize experimentally this vortex mode insulated metal transition. So you apply magnetic field, you have this artificial pinning potential, red spikes positions of strong pinning centers, these antidots, and then if you now apply magnetic field, so this is so-called first matching field, where you have exactly one flux quantum per each sharp and deep pinning center, and here at this position the number of carriers, in our case vortices, is exactly the same as number of localizing potentials, in our case these antidots. And if you have now more vortices than pinning sites, then other vortices cannot be pinned here, so they are forced to occupy interstitial positions, and pinning potential here is very shallow for temperatures close even to TC. There is no localization of these vortices. So these vortices, interstitial vortices, are metallic, and localized vortices are insulating in that sense. So therefore, in that sense, you have extremely sharp insulator metal transition. And these days, thanks to several important papers by Valeri Vinocourt with co-authors, so this is now a rapidly growing field concerning MOT-like transition for vortex matter. So now, as I told you, so if you have this stuff, then first of all you can visualize what is this really MOT insulating phase. So here, this is a simulation, right? So, and I'm telling you that vortices are sitting here. But having in hand good working scanning hole problem microscope, we first have this one. This is topography. We know exactly positions of all pinning centers. And then you scan the same area with scanning hole probe microscope, and then you nicely, this is not simulation, this is real image, so practically no noise, and these are singly quantized vortices. If you make antidots bigger, then we see also doubly quantized vortices. And if you increase so-called saturation number, maximum number of flux quanta per pinning sites, then you see also vortices appearing here. But now we will use this sample in order to observe these magnetic dipoles. I've started from this stuff, so you still remember that. But here we have had only spurious pinning centers, and we didn't control the position, and we didn't control the strength of these pinning sites. And then you have formation of these vortex-antivortex dipoles, as we have seen already. Now with this one. So it's much better defined structure. And now we scan it in Meissner layer, and we see beautifully these dipoles, vortex, antivortex, vortex, antivortex. If I cut this profile, then I see this field profile here. So it's very well defined, and indeed they appear where they should appear. So if I make a zoom, then of course I can calculate the fields carried by these vortices and antivortices. And then I can calculate vorticity, and I can also calculate visualize the penetration of these vortices and antivortices into a superconductor as we increase magnetic field. So this is zero magnetic field external, this is sample boundary, and then this is direction of the Meissner current, so it flows parallel to the sample boundary, and then here you see emerging vortex, antivortex, vortex, antivortex. And they are dying out as you go deeper into the superconductor, because there Meissner current is weaker. So now, if you increase magnetic field further on, then you see very bright vortex, antivortex dipoles, and then of course you define field profiles, and from field profiles you integrate, you extract vorticity using monopole model. And you see that you do not have just quantized vorticity like 0 and 1, but all the values in between are allowed. So this is again very nice result, but it's in no contradiction with any quantization rules in quantum physics here, because I'm coming back to this picture. Where is it? Yeah, this one. So again, I repeat, if this is my antidote, perforation in the sample, then any closed contour here does not enclose neither vortex nor antivortex, but closed contour like that involves both of them. And in order to involve into the circle only one of them, I have to cross this no-go zone, where I don't have superconducting material. I may not allowed to do so. So therefore, there is no controversy here. So flux can be anything for these objects, and as we nicely see, indeed, they are not quantized, but it forms a continuum, and you have always here balanced plus something, minus something. And it doesn't matter that they are not quantized, because plus something and minus something, if you add these two values, it's exactly 0, and 0 is for sure integer number, okay? So no catastrophe with flux quantization here. And actually, It's interesting also, but you may have these objects in any non-singly connected superconducting defect. So a superconductor with defect, and in that case, I repeat, at the edges of that defect, you create something which is not quantized. So in a certain sense, you can speculate that actually, if you have somewhere in space a black hole, and then close to that you try to generate something else, then this something else may appear with plus sign and minus sign, and it will not be quantized. If it's not quantized, it's classical. So in principle, this naive argument shows you that close to black holes you can generate matter which is not quantized, classical matter. But it's too far-fetched. Don't pay too much attention to that. All right, so then again this simulation. So important point is to focus on this. These are vortices and these are antivortices. You drag them out from this antidote, and in the beginning they are very pale. So they are not quantized. Then they grow in intensity and then become singly quantized, they're dragged away. So this is actually very nice stuff. And that's how it goes. Okay, I don't have too much time, I skip this one. So for that part, we visualize this vortex mode insulator state, and we have visualized magnetic vortex dipoles which are generated by Meissner current flowing around pinning centers. Now about vortex streets, what is that? And these are about Karman vortex streets generated by supercurrent flowing around pinning centers induced by the stream tip. So scanning hole probe microscopy, we have seen it already. Mode insulator, we have seen it already. Okay. Now vortex street. What is that? So this is an illustration of vortex street. So this is a flow of gas or liquid, and this is a rigid object. And then liquid or gas wants first to flow this side, then it generates vortex. And then this side, it generates antivortex, then this side and this, and then it's a sequence +1, -1, +1, -1. Very nice stuff. And they're called Karman or von Karman. Theodor von Karman was born in Hungary in 1881 in Budapest. And then in 30s, he immigrated via some other European countries to the States, working a lot in the United States, and then came back to Germany after the war, where he passed away, aged 81, in 1963, not far from Leuven in Aachen, in Germany. So, and he considered mathematics and all tricks related to flow, turbulence of gases and of fluids. And if you have here relatively high Reynolds number, then you generate alternatively vortex, antivortex, vortex, antivortex. If Reynolds number is quite low, then you generate always them simultaneously here. But that's not very interesting. This one is quite interesting. You can generate them in your kitchen experimenting with soap films, which is very, very interesting. So you see that you have an object, and then soap film flows, and it generates nicely vortex, antivortex, and these patterns are really beautiful, much better than some abstract paintings, which are extremely expensive. Okay, it costs you less than €1. And nature is full of surprises. So this is you are strong in geography. This is Baja California. And this is an island close to that, and the wind blows, and you see here this one, vortex, and then you have antivortex, vortex, antivortex, vortex, antivortex. Then you can do it at another location closer to Portugal and Spain. These are Canary Islands. So these are islands, and then this is island, this, and you see this vortex street, this one, this, generated by 3 different islands in the atmosphere. So what we have seen, that's cluster formation with STM, so I'll skip this part. Again, we have already discussed it. Now, what you expect with this vortex, antivortex stuff in case of superconducting materials? So in case of liquids and gases flow, we have seen it already here this vortex, antivortex, vortex, antivortex shown here in this red and green colors. However, these are not really charged gases or fluids, and no magnetic field is applied. If you do similar things for superconductors, there you have vortices and antivortices can be generated around such object, and if you apply magnetic field, they are dragged, of course, you have this magnetic field, they are dragged in opposite direction. So vortices will be dragged like that, antivortices are dragged like that. So therefore, we were able to generate with a STM hotspot like this one at any desired location. And then after that, we were scanning with scanning hole to see possibly flow of vortices and antivortices under the influence of Lorentz force. Here you have applied current or Meissner current, and hopefully you can see von Karman Vortex State in a very exotic way, not like that, but like that. So we were looking for that for quite some time, and then indeed, in the end, we were able to see this, and this one is also here. Sometimes 3, but 3 is very rare. So therefore, we are convinced here, we did also some Ginzburg-Landau simulations confirming that in case of vortices and superconductors, so this von Karman Vortex State is wide open. So, very exotic stuff. So this we have seen already many times, so I don't show this. And this one is moving to conclusions that basically, again, playing around with a combination of cheap STM. This is the corner of our scanning hole probe, and then visualizing local fields. First of all, we directly visualize distribution of fields for vortex mode insulator, and it's indeed as anticipated like that. And then we have found unusual form of Karman Vortex State. It doesn't go like that, like for normal Vortex State, but rather this way. So with that, I would like to stop and to thank all of you for your attention. Thank you very much.
Any questions?
What is velocity of the vortex center?